Hello friends, this is Professor Rahul Krishna Jibavne, and in subject of heat transfer, today we are going to see heat transfer by force convection. So the basically convection is divided in two parts. One is a force, second is a natural convection. And whenever as an engineer you are going to design any cooling system, so definitely we first focus on natural convection. If a natural convection is sufficient to maintain the temperature, then we don't go for forced convection, because forced convection definitely require any external means. That means fan, blower, any kind of external means which used to flow fluid forcefully. So definitely it required energy consumption. So cost will be increased for force convection. So whenever we try to design any cooling system, we first try for natural convection. If a natural convection fails to maintain that particular temperature, then only we shift to forced convection. If natural convection is sufficient to maintain the temperature, then unnecessary using forced convection will cost more. So basically there are two kind of convection: forced convection and natural convection. So here, as in picture it is seen that in natural convection, suppose any hot egg is kept in a room air. So room air will come in a contact of this hot eggs, then its density decreases, low density air will flow upward, and the vacant space will be replaced by surrounding high density air. So this will continuously flow, and continuously heat is carried from these hot eggs until these hot eggs and surrounding air temperature come in a equilibrium. And this continue air motion due to density difference, that is called current, convection current. Okay. And in forced convection, we don't wait for density difference. In forced convection, we apply any kind of external means with the help of which we blow air or fluid. In many time, uh, to have a tea, so we many time we blow it first before taking a sip. So that is also a application of forced convection. So forced convection, we forcefully allow fluid to pass over the hot surface, then it will carry heat and move ahead. And definitely this is, we experience that forced convection carrying heat much more than natural convection. So definitely Q, heat transfer by forced convection, is higher than heat transfer by natural convection. So let us see what is the difference. So forced convection, natural convection. First point is, in forced convection, a method of heat transfer in which the motion of fluid is influenced by external means. So external means, it may have any blower, fans. In natural convection, a method of heat transfer in which the motion of fluid is influenced by natural means. And natural means, it is nothing but a density difference. Second point, fluid motion generated as a result of an external source such as pumping, fans, suction device, etc. And in natural convection, fluid motion generated as a result of the change of the density of the fluid when heated. So whenever a fluid come in a contact of hot surface, its density decreases and it lifts up. Correct? Then in forced convection, only external factor can cause heat transfer. So it means, suppose we are using a fan. So heat transfer rate depends on the fan speed. So external means or external factor actually affecting the rate of heat transfer. No external factor affect the heat transfer, because it is by natural means. So it is only due to the density difference. So unless that fluid density decreases that much, so it can be move ahead. So we have to wait, correct? So it is simply purely a natural convection. So rate of heat transfer always lesser than forced convection. For the same temperature difference, forced convection transfer more heat than natural convection. And for the same temperature difference, natural convection transfer less heat than forced convection. To elaborate this, imagine there is a one hot plate is there, and hot plate surface is suppose 100 degrees centigrade, and surrounding air is 30 degrees centigrade. Now in natural convection, we kept that 100 degrees centigrade plate in a open air, so it takes a lot of times. But suppose same 100 degree centigrade plate is there and same 30 degree centigrade air, but that air we are using one blower, and 30 degree centigrade air we are forcing on that plate with the help of blower, so it will cool down fastly than natural. That means heat transfer is more for the same temperature difference if we go for a forced convection. Force convective coefficient is always higher because Q is directly proportional to H. Newton's law of cooling, Q is equal to HA, temperature difference. So if we compare heat transfer rate and convective coefficient, so Q is directly proportional to H. So in forced convection, heat transfer rate is more, so convective coefficient value is higher. In natural, convective coefficient value is lower. And the last point is example. So forced convection example is air conditioning or steam turbine. Natural, it is just simply keeping any hot object in open air, or even though suppose you kept any cold drink bottle or can outside, so it gain heat. Okay, after some time you found that cold drink is not enough cold because it gain heat from surrounding. So that is by natural convection. So this is the main difference. Many times it is asked to differentiate between forced convection and natural convection, and it is asked for 4 marks. So at least we have to write 5 to 6 points. Now in forced convection, before we go for any numerical, we must check out the various dimensionless numbers which is used during solving a numericals. Dimensionless number, why? Because it don't have any unit, it is unitless. First number is a Reynolds number. Remember friends, whenever in your numerical there is a Reynolds number, so definitely that numerical belongs to the forced convection, because in natural convection Reynolds number does not exist. Okay, so whenever there is a Reynolds number, that means that particular problem or that concept is belongs to forced convection. Now what is the Reynolds number? So Reynolds number is the ratio of inertia force to the viscous force in the velocity boundary layer, because this portion is already covered in your fluid mechanics also. So Reynolds number, inertia force upon viscous force. So if I put the mathematical expression for inertia force, so it is rho into velocity square. Viscous force is it is mu v divided by characteristic length, where mu is dynamic viscosity. Now here v and v square get cancelled, so we get rho v, and if I shift this characteristic length in numerator, so rho v LC upon dynamic viscosity. So density, basic unit is kg per meter cube, velocity in meter per second, characteristic length, diameter of pipe in meter, if it is a circular section. Okay, if it is a rectangular section, then characteristic length will be the different. So, but characteristic length must be in meter. Then dynamic viscosity, so kg per meter second. And what is the importance of that Reynolds number? So Reynolds number is used to categorize type of flow, whether it is laminar or turbulent. Okay. Many times external asks, or even though in exam also it is mentioned that define Reynolds number and give the significance of it. So significance means its importance. So what is the significance of Reynolds number? So first is Reynolds number is used to categorize the types of flow, whether it is laminar or turbulent. Higher Reynolds number means inertia force are higher than the viscous force. Viscous force, what is the role of viscous force? So viscous force try to stick a layer of fluids, and it is not allowed to shift the layers, and it tries to bond and try to flow with all layers at a time. So that is the inertia force. In a general language, we can say a frictional force between two layers of a fluid. So when inertia force is higher than the viscous force, then we say it is a turbulent, because viscous force try to restrict the layers to travel with a relative velocity. But if viscous force is lesser than inertia force, so that layers will travel randomly and we get the turbulent flow. But lower Reynolds number means lower inertia force and higher viscous force. So higher viscous force, so it not allow layers of fluid to travel randomly, so we get a laminar flow. And categorize, so Reynolds number is lesser than 2300, so flow is definitely a laminar. Greater than 4000, then it is turbulent, and in between 23 to 4000 it is a transitional flow. Correct? This is a generalized, and we know everything this, but remember, whenever there is any numerical and if they provide a data for laminar flow RE is 5000, that times we have to consider Reynolds number lesser than 5000, then it is laminar, because it is given for that particular numericals. Okay. Next dimensionless number is Prandtl number, and it is denoted by PR. Prandtl number is the ratio of velocity diffusivity to the thermal diffusivity. We know what is the thermal diffusivity, alpha, and the first unit where thermal conductivity portion is there. After that, we study what is the thermal diffusivity, and velocity diffusivity is nothing but a kinematic viscosity. So it is the ratio of kinematic viscosity to thermal diffusivity. Kinematic viscosity denoted by nu and thermal diffusivity alpha. Kinematic viscosity, dynamic viscosity divided by density, mass density, and alpha, that is K upon rho Cp. So here rho get cancel. So we can simplify this formula. And what is the significance of this Prandtl number? So it provides a measure of relative effectiveness of momentum and energy transport by diffusion in velocity and thermal boundary layers respectively. So this is the significance of Prandtl number. Next is Nusselt number. Nusselt number, it is denoted by Nu, and it is the ratio of heat transfer by convection to the rate of heat transfer by conduction. So convection upon conduction. So Q by convection divided by Q by conduction. So rate of heat transfer by convection, we know it is by Newton's law of cooling. So H, surface area delta T. Rate of heat transfer by conduction, so it is according to Fourier's law. So KAC delta T by L, because dt by dx. So here we are mentioning length of path. So if we consider that is surface area and cross section area is same, so that get cancelled. Temperature difference, for the same temperature difference, so delta T get cancelled, so we finally obtain Nusselt number is H upon KL. Definitely this L is stand for characteristic length. So simplifying this, so Nusselt number is HLC upon K, and this is similar to our Biot number, correct? So HLC characteristic length upon K. Now what is the characteristic length? Imagine force convection having a flow along suppose over one rectangular surface, and rectangular surface having a length L. So if a flow is along the length, so characteristic length will be that length of rectangular plate. If the flow is along the width of rectangular plate, then characteristic length will be width. If the flow is along the thickness of that rectangular plate, so characteristic length will be the thickness. Okay, I am talking about the external flow. Now Saturn number. So Saturn number is the ratio of convective heat flux of fluid to the heat transfer capacity of fluid. So convective heat flux H into delta T, then heat transfer capacity of fluid rho V Cp up into delta T. So delta T get cancelled. We finally obtain Saturn number is H upon rho V Cp. Now it is very difficult to identify because Saturn number is not in any standard terms. So make it to simplify and standard notation, we multiply and divide LC, that is characteristic length, by thermal conductivity K. So multiplying characteristic length thermal conductivity, dividing characteristic length thermal conductivity. So original value does not change. Now we will rearrange this. So first is H LC upon K, and second denominator rho LCV Cp upon K. So multiply and divide by dynamic viscosity. So again we are multiplying and dividing numerator only. Okay, sorry, denominator only. So denominator mu upon mu. So H LC upon K, we know what is this. Then rearranging rho VLC upon mu multiply by mu Cp upon K. So numerator is nothing but a Nusselt number. Remember, in fourth unit, Biot number does not exist. Even though the mathematical expression is similar to Biot number, but in fourth unit, it is a Nusselt number. And this first bracket belongs to Reynolds number, and this second bracket belongs to Prandtl number. So what is a Saturn number? So Saturn number is nothing but a ratio of Nusselt number to the product of Reynolds number and Prandtl number. Now the characteristic length. As I said, for external flow, when flow is over any surface, so whatever be the flow direction dimension of that surface, if it is along the length, so characteristic length will be the length. If it is along the width, then characteristic length will be the width. But imagine force convection is there, and many times in force convection we use closed pipe sections, just like a water flowing through a pipe, correct? So boiler tubes or your pneumatic pipes. So fluid forcefully flowing through most commonly through a closed channel, that is a pipe section. So whenever we talk about internal flow, internal force flow, then characteristic length does not exist for that internal flow. That characteristic length is called as hydraulic diameter, then that is DH. It does not change the soul of the formula, we just replacing characteristic length by dh. If it is an external force, definitely we will mention characteristic length LC. But if it is an internal force, flow through any closed channel, just like a pipes, then we have to replace that characteristic length by hydraulic diameter. Now, what is the hydraulic diameter? So, hydraulic diameter is 4 times cross section area of flow divided by weighted perimeter. So, whatever be the answer is the hydraulic diameter. Now, so 4 times cross section area. Remember, cross section area of flow divided by weighted perimeter. This is not a simple perimeter. This is a weighted perimeter. Weighted perimeter means the perimeter which is in actual contact with the fluid. That is the weighted perimeter. Now, suppose first case, circular pipe with a inner diameter D. So such kind of pipe is there, and force flow is there, and this flow passing through this pipe having an inner diameter D, and when it pass through this pipe, so it will touches this inner surface throughout. So what is the weighted perimeter? So weighted perimeter will be the pi d, correct? So here hydraulic diameter is 4 cross section area divided by weighted perimeter. What is the cross section area for this pipe? So it will be pi by 4 d square. And what is the weighted perimeter? So flow going to touch throughout the inner surface, so it will be pi d. So d and square get cancelled, pi get cancelled, 4 get cancelled. So hydraulic diameter for this simple circular pipe is diameter of pipe. Next, imagine there is a flow through annular space. Annular space means like this. There is one inner pipe section, circular, outer pipe section, and fluid flowing through the annular space between this. This is the most common example in your heat exchanger, where cold fluid passing through inner pipe, hot fluid passing through outer pipe. So in such application, we have to use a hydraulic diameter. So when flow is through the annular space, so hydraulic diameter basic formula 4 cross section area upon weighted perimeter. Now what is the cross section area? So cross section area of flow. So cross section area of bigger diameter pipe minus cross section area of inner diameter pipe. So it will give the cross section of only annular space. So pi by 4 d square minus pi by 4 small d square. So this is the cross section area of annular space divided by weighted perimeter. So what is the weighted perimeter? So this flow going to touch inner surface of this bigger diameter. So pi capital D. Also this is touching the outer surface of smaller diameter pipes. So again pi D. So weighted perimeter is addition of these two. So weighted perimeter is pi D plus pi of small d. This is the weighted perimeter. Now in this case, if I put the notation, so on simplifying, I observe that for such kind of problem, annular flow, hydraulic diameter is capital D minus small d. Okay. If you don't remember the final form, so go with our main format, that is hydraulic diameter is 4 times cross section divided by weighted perimeter. But remember, weighted perimeter means the perimeter where actual fluid touches. Now suppose it is not a circular pipe, it is a rectangular. Now I am taking only the rectangular. It might be a pentagonal shape, hexagonal shape, triangular shape, any kind. So we have to remember only the basic formula. Hydraulic diameter is 4 cross section area divided by weighted perimeter. So suppose there is a rectangular pipe section having a width W and height H. So in this case, what is the cross section area? So 4 cross section area is H multiplied by W, height into width. and divided by weighted perimeter. So weighted perimeter is twice of H plus W. So this is the weighted perimeter. So on simplifying, we observe that hydraulic diameter for this rectangular section twice HW upon H plus W. In this way, for any triangular shape or pentagonal or hexagonal, any kind of pipe is there, we can find out the hydraulic diameter. And this hydraulic diameter value we have to replace as a characteristic length. And again, I am repeating, hydraulic diameter is only used when the flow is through any closed channel. That channel might be a circular, might be a rectangular, might be a triangular, any kind of. If external force is flow is there, then definitely it is remain characteristic length only. But internal flow is there, then we have to replace hydraulic diameter. Now let us see one numerical to get more familiar with this concept. This is the last portion of our today's video. So numerical is air at 2 atmosphere and 200 degrees centigrade is heated as it flows at a velocity of 12 meter per second through a tube with a diameter of 3 centimeter. A constant heat flux condition is maintained at the wall and the wall temperature is 20 degrees centigrade. Above the air, and the wall temperature is 20 degrees centigrade above the air temperature all along the length of tube. Remember, our air temperature is 200 and whatever be the wall temperature is 20 degree above air temperature. That's mean wall temperature is actually 220 degrees centigrade. Calculate heat transfer per unit length of tube. And second, increase in a bulk temperature of air over 4 meter length of tube. So first we have to calculate heat transfer rate per unit length, and secondly, if the air is flowing, so what is the bulk temperature, that is total mass of air, what is the temperature rise, increase in bulk temperature for 4 meter length of tube only. And they gives further use Nusselt number relation is there, Nusselt number. So many times it is given NUD, that means diameter, NUL, that means along length. So this is suffix showing only the diameter or length. So Nusselt number along diameter is 0.023, Reynolds number along diameter raised to the power 0.8, Prandtl number raised to the power 0.4. Also they given a property of air at 200 degrees centigrade. Specific heat 1.025, thermal conductivity 0.0386, dynamic viscosity 2.57 into 10 to the power minus 5, and Prandtl number they given 0.681. If they provide a Prandtl number value, so we will not calculate the Prandtl number value from our given data. So remember, whenever they provide any data directly as a given, so we have to use that value only. If I am going to calculate Prandtl number, so it might be 682, then our answer will vary. So they given a Prandtl number 0.681, so we will use only this value. Now this is our given data. First we have to calculate heat transfer rate per unit length. So definitely we have to use Newton's law of cooling. Q is equal to HA delta T, correct? But here force convection, so this kind of our problem statement is there. There is a one circular pipe, air flow is there at 2 atmosphere, temperature 200 degrees centigrade, velocity 12 meter per second. This pipe which is at a temperature 200 plus 20 degrees centigrade and inner diameter is 3 centimeter. So characteristic length of the pipe is 0.03 meter. This is the internal flow, so definitely we have to replace this characteristic length by hydraulic diameter. And as we just saw, hydraulic diameter for simple pipe is nothing but a diameter of pipe. So characteristic length is 0.03 meter. Now using ideal gas equation. Why we are using this? Because they don't provide a pressure. They provide a pressure in terms of atmosphere. So we will use ideal gas equation. Rho V is equals to RT. If it is PV is equal to RT. If it is rho V, then it will be rho V equals to MRT. So this is PV equals to RT. So what is this V? It is a specific volume. So specific volume can be written as 1 upon rho. Specific volume is meter cube per kg and density is kg per meter cube. So specific volume can be written as 1 upon rho. So P, pressure, 1 upon rho, density is equals to RT. R is a characteristic gas constant. So density is P upon RT. So density is P, they provide 2 atmosphere. 2 atmosphere means 2 multiplied by 1.0132 multiplied by 10 raised to power 5. So 1 atmosphere means this much. 1.0132 into 10 raised to power 5. So 2 atmospheres, so multiply by 2. Divided by characteristic gas constant 287 multiply by temperature. So remember we have to put the temperature in Kelvin. So 200 plus 203 kg per meter cube. Now Reynolds number, because Reynolds number required a density of air. So we calculated viscosity. So rho we just calculate 1.493. Velocity it is given 12. Characteristic length we know that it is a 0.03. It is nothing but hydraulic diameter 0.03 divided by dynamic viscosity. So it is given with a statement 2.57 into 10 to the power minus 5. So after calculating we observe Reynolds number comes 20913.62, and as it is a dimensionless number, so there will be no unit. Now Reynolds number is given. Now we know that if a Reynolds number is greater than 4000, so flow is turbulent in nature. Okay. So we will use our given Nusselt number. Remember, many times Nusselt number 2 correlations are given. In this particular problem, only one correlation is given. Otherwise, they provide 2 correlation. One for laminar flow, second for turbulent flow. So, as our comment is that Reynolds number is this much and the flow is turbulent, so we will use turbulent flow Nusselt number relation. But in this particular problem, they provide only one Nusselt number relation, so no need to search for other Nusselt number. So we will use a given Nusselt number correlation. So Nu is equal to 0.023, Reynolds number raised to the power 0.8, Prandtl number raised to the power 0.4. Reynolds number we calculated, so 2913.62 raised to the power 0.8, and Prandtl number they provided, so 0.681. After calculating, we found that Nusselt number is 56.407. Again, this is also dimensionless number. Now, we know what is the mathematical expression for Nusselt number. So, Nusselt number is HLC upon K. So, Nusselt number 56.407. H we don't know, convective coefficient. Characteristic length or hydraulic diameter is 0.03. Thermal conductivity is given 0.0386. So hence we obtain the value of convective coefficient 72.577 watt per meter square Kelvin, or you can write watt per meter square degree centigrade. So now we know the H value. Why we are doing all this exercise? Only to find out the H value. Once we get the H value, we can use Newton's law of cooling. So Newton's law of cooling is H surface area temperature difference. So temperature difference is T surface minus T infinity. This is air temperature. So H, what is surface area? Pi d L. This is the total surface area, but they don't provide a length. So we will shift this length, so it will be Q by L. So H, now pi d, surface temperature minus T infinity. Put the value, we have the H values 72.577, pi d 0.03, temperature 220 minus 200. So hence we obtained Q by L, heat transfer rate per unit length is 136.81 watt per meter. This is our answer first. Secondly, they asked to find out the increase in bulk temperature over the length of 4 meter. That means delta T for that air bulk. So we denote suffix B. Now mass flow rate. Remember, it is a force convection. So whatever be the air is there, that air is continuously flowing. So there will not be a mass of air. There will be a mass flow rate. So mass flow rate, so density cross section area multiplied by velocity. This is the mass flow rate. Density cross sectional area pi by 4 d square multiplied by velocity. So density we calculated, diameter we know, velocity it is given 12. So from this mass flow rate is 0.01266 kg per second. As it is a flow rate, so definitely there will be per second, time is there. So mass flow rate is 0.01266 kg per second. Many times for mass simply it is denoted by m. For mass flow rate, m dot, on the top of m it is mentioned the dot. So m dot mass flow rate is 0.01266 kg per second. Now we know the mass flow rate. So rate of change of internal energy of that air must be equal to the rate of heat transfer. So rate of change of internal energy mCp delta T, but here delta T of bulk air. So mCp delta T of bulk, and rate of heat transfer, so Q by L per unit length we know, we just calculate in the first part, and they provide for 4 meter length. So Q by L multiply by length 4 meter. So M 0.01266, CP is given 1025, delta TB bulk temperature we have to calculate. Then Q by L 136.81 we calculate in first part and multiply by length of that pipe 4 meter. So we get the value, bulk temperature rise is 42.172 degrees centigrade. This is our answer. So thank you.